Before we tackle the very interesting and challenging issue of determination of hydronium ion concentration for a water solution of a hydrated metal ion acid, I decided to digress a bit and retreat to sulfide ion versus carbonate ion with respect to their relative Bronsted-Lowry base strengths. The acid-base table shows you that sulfide ion is one of our strong Bronsted bases. Carbonate ion, which is -2, just like sulfide ion, is a weak Bronsted base, not nearly as strong as sulfide ion. That tells us immediately, and as a reminder, we'll be looking at considerations like this in greater detail in Chapter 23. But since carbonate ion and sulfide ion are each -2 net charge, it follows that for sulfide ion to be a much stronger base, the negative charge density of sulfide ion must greatly exceed the negative charge density of carbonate ion. Now, if you're going to calculate charge densities, which we are not going to do, I think the way to do it is to take the charge, the absolute charge on the species, and divide it by its surface area. Because ion charge is, in essence, a surface property of the species. The negativity of the ion is not distributed throughout its volume. When an approaching positive ion comes to look at sulfide ion or comes to look at carbonate ion, it's looking at this minus charge that's on the surface. How concentrated is that minus charge on the surface? Well, again, since sulfide ion is a much stronger base, we know the minus charge on sulfide ion is much more concentrated. Not surprising, given that sulfide ion is a monatomic species, whereas carbonate ion is composed of 4 atoms. But let's take a closer look at assessment of the actual negative charge density of carbonate ion. Because if H plus approaches carbonate ion and makes a bond with carbonate ion, it does so by attaching to one of the peripheral oxygen atoms and makes, of course, hydrogen carbonate ion, or as we commonly call it, bicarb ion. It doesn't glue to a spherical entity and simultaneously contact and make bonds with, at least in part, each of the 4 atoms of this species. Again, it's a structure issue. So I wrote the only acceptable Lewis structure you can write for carbonate ion. Would you have been able to write this if I asked you to do this? Did you learn in 2045 that when you write a Lewis structure for a species which has got an even number of valence electrons, like carbonate ion, which has got 24 valence electrons total, which I describe as an even electron species. That means the species in question has got an even number of valence electrons. You add them up, is an even number. And most all species are in fact this. Because species which have an odd number of valence electrons are radicals. They have 1 or more unpaired electrons in their valence structure and are far more ready to make bonds, far more reactive than strictly even electron species. Because as you recognize, species which has got 1 or more unpaired electrons is not going to be noble gas electron structure. So right off the bat you'd expect it to be more reactive. Well, what I'm getting at with this remark is, did you learn in 2045 that if an even electron species contains carbon and or nitrogen and or oxygen as a component atom, where carbon and nitrogen are exceptionally common central atoms. No atom is more common central atom than carbon. Then when you go about writing a Lewis structure for these species, carbon, nitrogen, oxygen, provided the species which contains such is got an even number of valence electrons. Carbon, nitrogen, oxygen must be octet, period. Did you learn that? That's important, especially given that we now have on the order of 8 million carbon-based molecules known, more commonly called organic molecules. That's why we devote a whole year to study of organic chemistry by itself. There's a separate disciplinary entity in chemistry. I mean, there's a huge number of these carbon-based, structure-based molecules known. So if you're going to write Lewis structures for organic molecules, do you think you might need to do that in organic class? I like it when when my students come back to me after they've gotten in organic class and they say, I'm zipping through this because of what you put me through in 46. Some of them have even gone on to say, well, I hated you in 46. I hated you, you son of a bitch. I never had to work so hard in my life. But now I recognize the benefit of this. Because that's what this is for. I'm not going to be your false friend and give you a course which is easy to pass. Because if I do this, I am not teaching you chemistry. I don't know what the hell I'm doing, but teaching you chemistry, I am not. Because chemistry is damn tough. And I'm trying to give you a legitimate look at what chemistry is like. So if chemistry is damn tough, the course is damn tough. That's it. So if you want to waste time carping and complaining, so be it. But I would suggest strongly you spend your efforts in a far more fruitful fashion by doing something called study and learn. And forget the carping. In any case, back to this. If you also know that for even electron species, peripheral atoms have got to be octets, and wrote for this species carbonate ion, this Lewis structure, you'd have the requisite number of electrons, you'd have the right central atom, you'd have a species whose Lewis structure, the formal charges for all the component atoms would add up to -2. You're meeting with a lot of rules of the road. But for this picture, carbon is deficient of octet. So with that recognition, you know this cannot be correct. So you rewrite the Lewis structure I just described so as to show an imagined double bond at one of the carbon-oxygen bond sites. Wouldn't matter where you put it. Because you also know that once you see a Lewis structure of this nature, where you could just as well have sketched the double bond here or here, you're looking at a species for which this picture does not correctly represent its valence electron structure. To what property of this species do I refer implicitly? It's called resonance. Very important property. In particular in organic chemistry, because a whole lot of organic species have stability based on resonance. Or I should say better, stability attributable to resonance. So, with this picture before us, I now know that the reason why this Lewis picture is not an accurate representation of the overall valence electron structure for carbonate ion is that for carbonate ion, is there a carbon-oxygen double bond? Yes or no? No! Are there carbon-oxygen single bonds? No! And therein lies the rub of the grin with respect to this picture and the misrepresentation it casts on the true valence electron structure for carbonate ion. But it's still the best Lewis picture you can write. But you have to now use your imagination, recognize what resonance is all about, and realize that each and every one of the carbon-oxygen bonds in the carbonate ion has a bond length and strength that's stronger than a carbon-oxygen single bond and shorter than a carbon-oxygen single bond, but longer than a carbon-oxygen double bond and weaker than a carbon-oxygen double bond. What's the carbon-oxygen bond order? You learned bond order in 2045. Let's put it to use. You remember how to get bond order? Put your hand up if you don't know what bond order is. Don't be shy about this, because we got to get at this stuff. Bond order is a numerical measure of bond strength. Okay? Single bond, bond order of 1. True double bond, bond order of 2. Triple bond, bond order of 3. Right? Well, what's the carbon-oxygen bond order for this species? To get at that, given that resonance is a very important property of this species, you take the number of like bond sites which are under consideration, that's 3, and count up the total number of bonding electron pairs illustrated by your Lewis structure. That's 4. So, numerically, carbon-oxygen bond strength is 4/3 bond order. Stronger than a single bond, which got a bond order of 1, and weaker than a double bond, which got a bond order of 2. Okay?
What's the denominator again?
This is the number of bond sites. 1, 2, 3. Bond site is this location in space between atoms, where one or more bonding electron pairs is residing, as shown by your Lewis picture. Okay? Number of bonding electron pairs divided by the number of bond sites you are considering. How many saw this in 2045? Well, I'm going to tell you this. If you took 2045 laboratory, you saw this. If you paid attention to assignment 6 in its entirety, assignment 6 for 2045 laboratory, I commonly refer to as the Tinker Toy experiment. Because you get out your model set and you make models, like playing with Tinker Toys. You put sticks in the spherical shaped things and simulate bonds. Then you take another spherical shaped plastic entity and glue it to the other end of the stick. Now you've shown a diatomic molecule. And away you go from there. Now then, the charge density issue. If, for the best Lewis structure we can write for carbonate ion, if for this Lewis structure we calculate formal charge. Do you remember that? Formal charge is a device which you use to constructively criticize a Lewis structure after you've written it. Remember that? I say again to you right now, you're responsible for all this stuff in every detail to which I have just referred. And if you need review, it's all in your notes in chapter 23. I'm sorry I don't remember the page number, but damn it, I think you can find it. All what I'm talking about is there. Writing Lewis structures. How to interpret them in light of hybrid theory and VSEPR so you can get at hybridization and geometry. It's all there in chapter 23, and you need to know it. We reminded you time and again. The most important property of a species is its structure. What's the actual formal charge on each oxygen atom? Remember, since this has resonance and the true bond order is 4/3, every one of these oxygen atoms is electronically equivalent. Each oxygen is in an identical valence electron environment. There ain't no double bond and there ain't no single bonds. So with that, I repeat my question. What is the true formal charge on each oxygen atom for the carbonate ion?
-2.
Correct. The total formal charge borne by oxygen minus 2. But you got 3 electronically equivalent oxygens. So watch out for this very challenging arithmetic. Total charge of minus 2 divided by 3 equivalent, electronically equivalent oxygens. That gives you a charge of minus 2/3. So here's this sulfide ion with a charge of minus 2. You think that might attract more strongly something plus than something which is really looking at something plus with a charge of minus 2/3 on each of the atoms that this plus thing might approach? How about that? We're going to do a lot more of this stuff in chapter 23. We proceed. Regarding determination, calculation of hydronium ion concentration for water solutions of Bronsted-Lowry polyprotic acid, we now look at the most interesting and most challenging case of such. Hydronium ion concentration for a water solution of a hydrated metal ion acid. For the specific case of 100th molar ferric nitrate solution. Now, I hope you remember forever that if you're going to do chemistry on a system like this solution, what do you got to do first?
Write the PSI.
Write the PSI! You betcha. Because if you don't know what the hell you're dealing with, there's no way you can understand the chemistry which the system exhibits. Now, I've written the PSI for the species of concern. But in addition to the species of concern, we also in this system have nitrate ion and ever so obviously water molecules. Fe plus 3. A metal ion with an appreciable positive charge density. Upshot, when you dissolve a source of Fe plus 3 in water, like ferric nitrate, these Fe plus 3 ions do not swim about by their lonesome. They make strong coordinate covalent bond interactions with neighboring water molecules to form the species hexaquo iron plus 3, a species whose formula you see in our acid-base table. A species which has got a Ka value of 4.0 times 10 to the minus 3. That's a pretty damn good weak acid. Good deal stronger, for example, than acetic acid. So, we know if we're going to get the hydronium ion concentration calculated for this solution, we got to write this ionization equilibrium. Now, just to save time, Fe plus 3 with quotes on it is really that thing. Okay? So this reacts, makes hydronium ion, and makes Fe plus 2 with quotes on it, which is really this thing. So I don't have to keep on writing out these long formulas. And now, as we did with sulfuric acid, as we did with H2S and hydrated CO2 and phosphoric acid and whatever have you, we wrestle with the question, is there another source of hydronium ion in the system with which we must be concerned to calculate this hydronium ion concentration correctly? For sulfuric acid, that was not difficult because the first ionization reaction was not controlled by equilibrium. It was 100%. So I had to pay attention to one equilibrium. For the sulfuric acid solution, that was the ionization equilibrium of hydrogen sulfate ion. When we dealt with the polyprotic molecular acids, where the parent acid was weak, even for something like triprotic phosphoric acid, calculation of hydronium ion concentration is easy because you only had to pay attention to Ka1. Because as we recognize Ka1 for any such acid, parent acid's molecular, for any such acid, parent acid molecular, Ka2 is a hell of a lot smaller than Ka1. So if the parent acid is also weak, you don't have to pay attention to Ka1 to calculate hydronium ion concentration correctly. Now let's look at Ka2 for this system, which corresponds to the ionization of this thing behaving as a Bronsted acid. Reacting with water, creating hydronium ion on establishing this equilibrium, and producing Fe+, which is this thing. There's Ka2 for this. 5.0 times 10 to minus 4. How does this compare to this? How do these Ka values compare?
Fairly comparable. Fairly comparable.
How comparable are they? Give me the number.
Ka1 is about 10 times more than...
I don't want about. I want exactly. But you're on the track, right track. How much? 8 times bigger, that's all. Surely you can take 4.0 times 10 to minus 3 divided by 5.0 times 10 to minus 4. Hell with that damn thing. I swear I'm going to run this course the way I want to run it one of these days and see what happens. No calculators permitted, period. The hell with this crutch. You need to learn this part of the language. And it's been taken away from you. Well, I want to restore it. If I had my way, and I've told the department this, before any student coming to the University of Florida would be permitted to take Chemistry 2045. And there's a whole bunch of you who need to take Chemistry 2045 because of the academic discipline in which you desire to major. Before you can take 2045, I don't care what high school you came from. I don't care if you come here with a 12.3 grade point average. I don't care if your 12.3 grade point average is in high school math class. I don't care if you took AP calculus before you got here. I don't care, because I don't believe a lot of this stuff. I don't believe anybody that comes here with a GPA that's above 4. I don't believe that. There's something wrong with this stuff. Everybody would have to take a test to get into 2045. Material supplied would be the test, pencil, and paper. No calculators. And the test would be strictly arithmetic. That's it. I mean it. No chemistry. Strictly arithmetic. With some word problems, which would have to be solved with arithmetic. And there'd be no multiple choice. You'd have to write out your solutions so we can see what you're thinking. And until you pass this test, you ain't getting into 2045, period. And by golly, this calculator crutch syndrome that has been killing us for 30 damn years now would be dealt with. I'd hit that right on the nose. Because a whole lot of folks wouldn't pass this test. And then they'd complain. And mom and dad would call up the dean and say, "What's going on? My son has a 14.8 grade point average from high school and can't get into your chemistry class." Well, your son can't do arithmetic. But. He can't do arithmetic. Can't pass this arithmetic test. Guess what? All this fuzziness would clear up soon. Because you're all capable of doing this. I know that. I know you have the intellectual capacity to do that. But if you don't do it, the skill gets very rusty, full of cobwebs. And you got to get cobwebs removed. All right, enough of that sermon. You've heard it before, you'll hear it again. Upshot of this is the ionization of this second equilibrium before it comes, this ionization of the second reaction before it comes to equilibrium is considerable, especially with 100th molar. That's a fairly dilute solution. You remember that? ionization extent depends on Ka magnitude and 1 over m sub I. 100th molar iron nitrate solution. You see that K value? Do you see that K value? Number 2 K value is still bigger than Ka for acetic acid. And in 100th molar acetic acid ionizes to a significant appreciable extent. So guess what? What we are now realizing is that to correctly calculate the hydronium ion concentration for a hydrated metal ion acid solution like this one, you got to consider Ka1 and Ka2, which we haven't had to do for the other polyprotic acids, but now we do. So at this stage of the game, after we've considered these two ionization equilibria, how many unknowns we got? Well, we don't know this. That's what we want to get. And we don't know this, because these are not equal, because this is also going. So we don't know this. And we don't know this. So I'll go question mark. Well, this is what we want to calculate, so I'll call that question mark. 2 question marks, 3 question marks, and 4 question marks. We got 4 unknowns and 2 equations. That's a problem. How do we solve this? Algebra has taught us if you have 2 simultaneous independent equations but 4 unknowns, you can't solve it. So we need more equations. What are these more equations that we need? How we get them? Well, one of them we've already looked at. It's called material balance. That's what MB is. See what I wrote here? Must consider Ka1, Ka2, those we have. MB, let's write MB for this right now. Write MB for this system. For the iron-containing species in this system. Write it on your paper right now. We'll call it MB for iron. Everybody write this? That's it. MB for iron. This tells us that I can always solve for any given iron-containing species in this system, which is or single asterisk or double asterisk or triple asterisk iron, Fe3 plus quotes, Fe2 plus quotes, Fe single plus quotes. I can always solve for one of these in terms of the other two. Okay? So now we have in essence reduced the number of unknowns to 3. But we're still stuck. We still need another equation. But before we talk about this other equation, I'm going to ask a question. And for you in 46L, when you get to assignment 10, which is strictly for extra credit, whatever points you earn goes into your point bank. Same for assignment 11 in 46L. In assignment 10, you're going to do some chemistry with iron nitrate solution. Maybe it's iron sulfate solution, who cares? But it's iron 3 in solution. This hydrated iron plus 3 is pale violet. A pretty violet, but not intense violet. Whereas when hydrated iron plus 3 reacts and becomes quote-unquote Fe2 plus or quote-unquote Fe plus, these hydroxyl complexes, this is a monohydroxyl complex, this is a dihydroxyl complex, these are each yellow-brown in color. If you make this solution in the laboratory and observe it, what color do you think you will see?
Yellow-brown.
A vote for yellow-brown. Any second votes? Supporting votes? I vote for yellow-brown. Hey, these K values are telling us, in conjunction with the fact that this is a fairly dilute solution, these equilibrium reactions, before the equilibrium is established, are going extensively left to right. And this yellow-brown is a more intense color than pale violet. That's what you're going to see. So simple observation of the solution is telling us this equilibrium is proceeding substantially left to right as written, and this one is probably proceeding substantially left to right as written. And based on our analogy of this, or our comparison of this to Ka acetic acid, and the fact that we've already looked at acetic acid at various concentrations, and a note at 100th molar, it reacts to an appreciable extent, we know this thing is contributing to the hydronium ion concentration. We know we can't neglect this equilibrium reaction to calculate correctly the hydronium ion concentration for this system. That's why we need Mb, but we still need one more equation. It's called Cb, for charge balance. So I'm now going to write the charge balance equation for this system. It's in the notes, but chances are, if you've looked at it, you're probably puzzled by its origin. How the hell did he write that? I like it when students come to me with exams and quizzes and my notes, all of which I've written, and they say, this is what they want. I got news for you. I am they. I am singular. Now, I'm married, but that's got nothing to do with this chemistry business. But I am they. I write all these questions. Exams, quizzes. I've been teaching this 2046 stuff here at the University of Florida since summer of 1989 was the first time I did it. And before I came here, I taught it many, many times at Santa Fe College. And I had a chance to come back here to my alma mater, because I did my PhD here. I haven't told you that yet. Okay. Now then, charge balance. What does it depend on? I mean, it pretty much tells you what it depends on. It depends on the principle of electroneutrality. Oh, what I was going to tell you before slipped my mind. Well, all these times I've taught 2046. How many times do you think I've given the same quiz? How many times do you think I've given the same exam? I see faculty pull this. Oh, I got a file, I'll take one I wrote 4 years ago. I heard the answer. The answer is never. Never. Hey, I don't want my computer to get dusty. When I start pulling out stuff that I've already done, then my computer's turned off. I don't want that. I write a new original exam and quiz every damn time out of the box. Sure, once in a while I'll refer to a past question because I thought it was something that's necessary to be part of a given exam, but hey, new stuff all the time. In any case, back to this. Charge balance depends on the principle of electron neutrality, which says that any bulk chemical system, we've already told you this, now we're telling you again. Now it's officially. Any bulk chemical system which contains charged particles has got to be electrically neutral. That means total moles plus has got to equal total moles minus, period. And from that statement and no other statement, we can write a charge balance equation for any system that contains charged particles. And clearly this system contains charged particles. So here we go. And for this system, I also have the liberty of being able to set the charge balance equation, which stops here. I am able to set this charge balance equation equal to a charge sum. That's this number. Now then, fun. How many of you could have written this equation on your own without any commentary? How many of you are mystified by this equation? All right, let's demystify. All right? Let's take a simple case. One molar calcium chloride solution. PSI, right now. You write it. And for this system, I want you to write the PSIs in terms of molar concentrations. Okay? Never mind water, because it doesn't have a charge. Boy, this was tough. Really tough. See this? There's your PSI written in terms of molar concentrations. How many wrote that? That's nothing. That's a piece of cake. Now comes the charge balance part. Remember the statement? Total moles plus has got to equal total moles minus. And in calcium chloride solution, the only principal species present which bear charges are calcium ion and chloride ion respectively. So if I want to set the molar concentrations of these ions equal to each other. Total moles plus, because the only thing in here that's plus of consequence is calcium ion, and the only thing in here of consequence is minus is chloride ion. If I want to write an equation, if I want to equate these molar concentrations, what do I have to do? Tell me what I have to do. Multiply what by what? 2 times 1 is 2. Oh, that's not really toughy. You agree? Now I have an equation. Twice the calcium ion molarity is equal to the chloride ion molarity. 2 times 1 is 2. Wow! You know what that means? To write a charge balance equation, you first write the molar concentrations for everything in the system that's plus, and the molar concentrations for everything in the system that's minus, which I should think you immediately recognize as a total species inventory. PSI's principal species inventory. Most of the time you are going to be okay with the principal species inventory, but we're writing a total species inventory. For the calcium chloride solution we wrote a principal species inventory. For the iron nitrate solution, I've written a total species inventory. Okay? But you know how to play this game. Because after all, any water solution got hydronium ion in it and hydroxide ion in it. So they're always going to be part of a total species inventory for any water solution. You know this. And then you take each concentration term and multiply it by the magnitude of the charge. Isn't that what we did here? 2 times this. Okay? So all you got to do is sum up the plus concentration terms, the minus concentration terms, and take every concentration term and multiply it by charge magnitude. 3, 2, 1, 1, 1, 1, done.
What was the charge sum for calcium chloride?
Wait a minute. You want the charge sum? Tell me what it is, I'll write it.
2.
See? That wasn't hard, was it? You know it is. Here it is. Okay? What?
How did you find the charge sum without knowing the concentration for FE?
What do you mean I don't know concentrations?
Well,
You see this bottle label?
yeah, what's the difference in the bottle level? How did you know to multiply by 3?
Tell me, what is the nitrate ion concentration in this solution? What is it?
0.03.
Is that what I wrote over there? Notice that. In this solution, is nitrate ion present? Yes. Is nitrate ion present at a molarity of 0.030? Yes. And does the concentration of nitrate ion diminish when nitrate ion is put in the solution, in this solution, by nitrate ion reacting with anything? No. Nitrate ion's in there at a molarity of 0.030, and it doesn't engage in any other chemistry. It doesn't engage in any chemistry in the system. It's this good old spectator. It's going to swim around while all this fun stuff happens. And nitrate ion's going to say, gee, I enjoyed this game. And we're going to have chemistry referees. Not these people who foul up the NFL.
So where exactly did the nitrate come from?
It's there. It's in solution. I dissolved iron nitrate to make this, right? Don't forget that. That's the label on the bottle.
So does that mean the hydroxide concentration is equal to 0?
How can hydroxide ion concentration ever equal 0 in a water solution?
Well, I was thinking...
How can hydroxide ion ever equal 0 in a water solution? Okay?
But then how is the concentration of the nitrogen?
Now, hold on a second. I'm going to have you answer your own question. Is this solution acidic?
Yes.
Then tell me, what is the hydroxide ion concentration in this solution absolute maximum?
1 times 10 to negative 7.
If I add 1 times 10 to minus 7 to 0.030, am I going to change 0.030? Thank you. We see how to do this now? It's easy. Concentration terms, positive ions, negative ions, multiply by absolute magnitude of charge. That's all there is to it. Now guess what? I have written 4 simultaneous independent equations for a system which has originally 4 unknowns. Can I solve it now? Can I solve it now? You're damn right I can solve it now. Now then, would I hold you responsible for solving something like this on an exam or quiz? No. The arithmetic requirements are substantial. But I feel that I'm perfectly at liberty, for example, for a system like this, to ask you questions and pose problems which are about how to solve And what equilibria do I have to consider? How do I write material balance? What's the charge balance equation? And after having written the charge balance equation, can I set the charge balance equal to a charge sum? That can be tricky. We'll look at the details of writing a charge sum for a charge balance equation next time. But I want to leave you with this one. Just to be sure you've digested this charge balance equation writing. We've shown you it's quite straightforward. Look at the notes. Question 1857. I want you to write CB for principal species in 0.10 molar aluminum sulfate solution. I want you to write CB for all species in 0.010 molar aluminum sulfate solution. I want you to answer this question. Can CB be set equal to a charge sum? And how can CB for all species be simplified? So there's question 1857. 4 parts. We'll tackle this next time, recognizing that when you can do this, you are now in position to do a very powerful thing. You'll be able to take any water solution which contains species whose presence depends on pH and analyze that system so as to be able to correctly report the true mole quantities of every one of those species in the pot. That's pretty damn powerful.